Quantum computers, they hold this incredible promise to change literally everything, from medicine to making new materials. But there's a beast lurking inside them, a really fundamental problem that can turn all that amazing power into just chaotic mess. So let's dive into how scientists are actually taming that beast right now.
The whole challenge, really, it all boils down to this one question. Now, the noise we're talking about, it's not sound. It's more like a constant storm of errors. They're caused by the environment, by tiny little imperfections in the hardware, and even by the qubits themselves interfering with each other. This noise just corrupts the calculations, which makes it the #1 villain in the whole quantum computing story.
And this villain, this era we're in, it actually has a name. We're living in the NISQ era. That stands for Noisy Intermediate Scale Quantum. And it's this fascinating, kind of frustrating middle ground where our machines are way too powerful to ignore, but they're just too error-prone to be perfect. So the entire game right now isn't just about building more qubits, it's about managing the noise in the ones we've already got.
So how do we fight back? Well, it turns out there are two main strategies, and they form this really cool layered defense. First, you've got error suppression. Think of this like putting up a shield to proactively block errors from ever happening in the first place. Then there's error mitigation. This is like a cleanup crew that comes in after the calculation is done to statistically fix the messy results. You really need both to win this fight.
Okay, let's start with that first line of defense, error suppression. This is all about actively protecting the super fragile quantum state of a qubit while the computer is actually running. Think of it as real-time protection for your calculation.
And the techniques here are pretty slick. They're like a whole toolkit for active defense. For example, one method is like constantly spinning the qubit to shield it from background interference. Another one is this clever trick that basically transforms predictable, really damaging errors into random, much more manageable static. And a third one just makes the whole program run faster, which gives noise less time to creep in and cause trouble. It's all about protecting that qubit while it's doing its job.
But here's the thing. Suppression can't catch everything. I mean, no shield is perfect, right? So after we've run our noisy calculation, we have to call in the cleanup crew, error mitigation. These are some seriously powerful statistical techniques that look at the messy answer and figure out what the correct answer should have been all along.
Okay, one of the cleverest mitigation tools is called Zero-Noise Extrapolation, or ZNE, and the logic here is just brilliant. So first, you run your experiment and get a noisy result. No surprise there. Then, you do something that sounds totally crazy. You run it again, but you intentionally make it even noisier, and you do it by a precise amount. You might do this a few times, each time with a little more noise. Then, by plotting these increasingly wrong answers, you can actually draw a line straight back to see what the answer would have been with zero noise at all. It's a really beautiful and simple idea for a super complex problem.
But what's the cost of getting a mathematically perfect answer? Well, sometimes it's just staggering. The most powerful cleanup technique out there can require this much more computation to get the job done.
So yeah, that huge number comes from a technique called probabilistic error cancellation, or PEC. This thing is the ultimate weapon. It can deliver an unbiased, almost perfect result by running a massive number of extra circuits just to cancel out the noise. But as this quote shows, the cost just explodes. It grows exponentially as your quantum program gets bigger. It's the ultimate trade-off, right? Perfect accuracy for an enormous price.
Now, I know this all sounds incredibly complex, but here's the good news. For the developers who are actually using these machines, it's becoming so much simpler. All of these powerful tools are being packaged into software frameworks, like IBM's Qiskit Runtime, that make them way more accessible.
And this is just fantastic. Instead of having to program every little detail, a user can just choose a resilience level. Seriously, think of it like turning a dial. At level 0, you get the raw, noisy data, which is perfect for debugging. Turn it up to level 1, you get some basic cleanup. Level 2 brings in the heavy hitters like Z and E for real experiments. And then, level 3 unleashes that ultimate, high-cost precision of PEC. You just turn the dial based on whether you need speed or perfect accuracy.
So does this layered strategy, suppression and mitigation, does it actually work? Can it help us solve real problems? Well, the answer is a resounding yes, and it's leading us into a whole new era that people are calling quantum utility, where these noisy machines finally start doing some useful science.
And look, this isn't just a theory. In 2023, researchers put it all to the test on a processor with 127 qubits. And let me tell you, at that scale, things get very, very interesting.
And here is the payoff. Using that exact combined strategy, error suppression plus error mitigation. They were able to accurately simulate a really complex magnetic system. And as the research paper itself states, the calculation was, quote, beyond the reach of brute force classical simulation. I mean, even a supercomputer couldn't just muscle its way through it. This was a critical moment. It was proof that a noisy quantum computer, when you manage its errors properly, can give us valuable scientific insights that are otherwise completely out of reach.
So all of these techniques, the shields and the cleanup crews, they're creating a bridge. They're allowing us to do really useful work today, right now, while we keep building towards the ultimate goal, which is a truly error-free quantum future.
So, let's just recap that winning strategy one more time. You've got layer 1, that's the shield, real-time error suppression, protecting the qubits. Then you have layer 2, the cleanup crew, powerful error mitigation that mathematically refines the final answer. And putting those two together, that's the integrated approach that is the key to unlocking useful science from today's noisy machines.
So the crucial takeaway here is that we've found a way to tame the quantum beast. We can manage its noise and extract real value from it. But that leaves us with a final, really tantalizing question, doesn't it? Managing noise is one thing, but these techniques are really just a bridge to the true holy grail, fault-tolerant quantum computers that can physically correct their own errors in real time. We know how to manage the noise now. The question is, when can we finally eliminate it for good?